Hello and welcome back to our series of tutorials on how to use the scalable workflow execution engine Saasfee. As you might remember from the last demonstration, Saasfee comprises the functional workflow language Cuneiform and the highway workflow scheduler for Hadoop Yarn. In this demonstration, we would like to give you an introduction to Cuneiform. While Cuneiform workflows can be executed on top of Highway and thus Hadoop, this tutorial will focus purely on Cuneiform's language aspects and local execution mode. We will have a look at tools for creating and running Cuneiform workflows locally, including an interactive command line interface and an editor with visualization and debugging functionality. So let's dive right into it by starting a new terminal window. On the command line, we can enter cuneiform-h to get an overview over the options available for running the local Cuneiform interpreter. From the output of the help screen, we see that the interactive command line interface can be started by entering cuneiform-i. We can now play around with this interface by entering a few simple commands. By entering x equals to 5, we assign the variable x to have the value 5. By entering x, we query the value of the previously defined variable, which results in the answer 5. Next, we assign the variable y to be whatever x is by entering y equals x. When we now query the value of y, we, unsurprisingly, get the answer 5. Note, when we queried the variable x, Cuneiform returned the 5 in single quotes. The reason for this is that Cuneiform does not have an internal model for numbers or even booleans. Cuneiform has only one built-in atomic data type, the string. Currently, the variables x and y have the same value 5. Let's see what happens when we update the value of x to be 6 by entering x equals 6. By querying y, we find out that y has also been updated to be 6 by this reassignment. The reason for this is that Cuneiform has a call by name evaluation strategy. Thus, the internal representation of the variable y is not a memory cell holding the value 5 or 6, but the original definition we gave it, the expression x. Consequently, when we updated x, we also updated y. We can verify that this is the case by querying the special variable state. This query does not return a result but prints all definitions we entered into the command line interface so far. We can close the session with the Cuneiform interpreter by querying the special variable quit. While workflows can be created using any editor, the Cuneiform editor offers syntax highlighting, ad hoc error reporting and compile time visualization features. You can start the Cuneiform editor by entering cf IDE in a running terminal. The editor comprises 3 sections. The section in the bottom right is the main editing window. Here you can enter the source code for your workflow. The section in the top lists all the errors that have been detected. This error reporting panel is constantly updated while we type. The section in the bottom left shows information about the workflow that can be derived at compile time. For instance, the DAG tab shows the static call graph representation of the workflow, which is a useful graphical feedback during programming. Let's start with a simple hello world example. We define a task greet, which takes the name of a person as a string and returns a string in which we say hello to that person. To define a task, we use the def task statement, which expects a task name, in this case greet, a signature, that is the input and output, the foreign language in which we want to express the body of the task, in this case bash, and the task body enclosed in Mickey Mouse eared curly braces. In the signature, we declare the task to produce the output variable out while consuming the input variable person. The colon separates input from output variables. A task can have multiple inputs and outputs. Now, we call this function with the value Jane Doe. This looks like a common function call, with the only difference being that all arguments to a function have to be qualified. In this case, we state that we want to call the task greet by binding the input variable person to the value Jane Doe. Let's save this workflow as helloworld.cf. From the terminal, we can now run the workflow by entering Cuneiform helloworld.cf. After Jane Doe was greeted by Cuneiform, let's go back to the Cuneiform editor and do some more work on the workflow. Cuneiform has a built-in list data type which we can use to greet not only Jane Doe but many persons. Let us redefine the previous example in the way that the people to be greeted are held in a variable world. Saving and running this workflow makes Cuneiform invoke the greet task for both names. Note that we have defined the task greet only for a single person. But by calling the task with a list argument, we map the task greet over that list. By defining tasks in a way that they could potentially consume a list for any of their arguments, we can easily extend a workflow's input. In most instances, the workflow structure can be left unchanged if we need to analyze one more sample, map to one more chromosome, or apply one more algorithm. All that needs to be done is to add one more element to a list. Since we are free in the choice of the scripting languages in which we define a task, we can easily come up with a task greet written in, for instance, Python. Basically, no matter what language is best suited to solve a particular problem, we can seamlessly integrate it into the workflow definition. Before we conclude this demonstration, let us have a look at and execute a word count workflow similar to the well-known MapReduce example. The workflow comprises low-level functions for counting words in a text file, similar to a map, and for summing up the counts, similar to a reduce, in Python. The text data that is processed in this particular case is the set of the State of the Union speeches ever held by presidents of the US. Note that in contrast to the Hello World example, these functions now process files instead of strings. Let's execute the workflow from the command line. Since the output will not be a text, but a file, we should tell Cuneiform to create a summary of the workflow execution such that we get a handle to the file. Let's have a look at the result. Let's wrap up this demonstration at this point. We have learned some basic language features of the functional workflow language Cuneiform and have played around with different ways of using Cuneiform. If you would like to delve deeper into the language features of Cuneiform, I can warmly suggest reading up on the latest Cuneiform publications as listed on the Saasfee website. In the next tutorial, we will have a look at data-intensive, complex, real-world workflows and how Cuneiform workflows like these can be executed on a Hadoop installation using the workflow scheduler Highway. Until then, I'd like to thank you for your attention. Till next time.